Hello, everyone. Today, in the absence of Kiri, I think he has some personal business to do. We'll have Anna, the postdoc from Angola, to introduce us to the topics of cross-coupling. We're going to have half of the, not half, just a small portion of the class being on Choctaw. So for those that are joining online, I'll be just shifting the focus whenever Anna is going to write on the board. And if you have any trouble just visualizing anything that's written on board, just let me know through chat window. So I'll be just adjusting this a little.
Yeah, sounds good. Good morning. Yeah, it will just be mostly probably the problems of the day that we'll do on the board, since that'll be easier since I don't have to. I will just go through it on a PowerPoint slide. Yeah, so today's topic is catalytic cross-couplings. And we'll be talking about most of the talk will be on traditional redox-neutral couplings between one electrophile and nucleophile to form mostly carbon-carbon bonds, but we'll touch a little bit upon heteroatom carbon bond formation as well. I think this topic, most of you may have some, yeah?
Turning the lights down a little bit, please.
Sorry, what?
Turning the lights down a little bit.
Oh.
Sorry.
No, you're good. Yeah, so I think probably most of you, I think all of you have some familiarity with the cross couplings. Maybe you're running in lab, maybe you've gone through some of them, at least in other classes. So the lecture will kind of be on a historical perspective. We'll go through some of the history that led up to the discovery of these named reactions. And over here is the general catalytic cycle. So keep this in mind as we go through. Most of these are going through these elementary steps. Some modularity, maybe we'll talk about some details. Most of the details will be here in the transformation step, which is typically the turnover limiting step. So the metal goes through oxidative addition with your electrophile, then you have transformation, reductive elimination. So keep that in mind as we go through. We'll continue going back to this type of mechanism. Yeah, so the traditional redox neutral, you couple electrophile with nucleophile, very classic. There are also examples of oxidative couplings where you couple essentially two nucleophiles. And then you, of course, need to turn the oxidant to get your metal back on cycle. We'll see one example of this. And then similarly, reductive couplings between two electrophiles. Here, you of course need a reductant to get your metal back on cycle. We won't talk about these. There's been a lot of recent literature, kind of boomed in the reductive couplings the last 20 years or so. Specifically, and what you typically use as a reductant here are stoichiometric metals such as zinc or manganese, can also be chemical reductants. And then finally, we will talk a little bit about the conjunctive coupling. It's mostly just to keep this in mind that you can kind of interfere the classic cross coupling between the electrophile and nucleophile with Y. So we'll see a few examples of this at the end. All right. Yeah, so there's a few key reviews down here. For a good timeline, there's this review that may give you, if you're interested in looking more into some of the early work. And most of these classical or traditional cross couplings were initially found with nickel. And then maybe because palladium had some, at the time, the interest in different types of couplings, the way of handling palladium, the predictability of palladium chemistry may have led to it switching from a nickel catalyst to palladium. We'll see a little bit about that. So palladium has much more predictable chemistry. It does a lot more 2-electron chemistry. Nickel likes to do 1-electron chemistry, as you may have seen before. And then ligand scaffolds for palladium were more intuitive and it gave really high turnover numbers compared to nickel and high yields. So that's why it's shifted to palladium, and that's also what was rewarded with the Nobel Prize in 2010 was the palladium catalyzed cross-coupling, or the development of that. All right. Yeah, so we'll start very classic with carbon-carbon bond forming reactions. So before we go into catalysis, I just want to show a few examples of some of the puzzle pieces that were already published in literature prior to a catalytic approach being published a few years after. So this example from Chat and Shaw in 1960, where they have this nickel bisphosphine complex, and they treat that with a Grignard reagent. And what do you think is going to happen here? Yeah, go ahead.
Transmetallation.
Yes. So you transmetallate to form the corresponding RR nickel complex, in this case trans, and what is the byproduct?
Just magnesium bromide.
Yes. And what drives the reaction?
And precipitation.
Yeah, this is the thermodynamic driver for this reaction. So this was early work all the way back to 1960. This was published documentarily. So already here, we see an example of a transmetallation possible with a Grignard reagent. Next example here is then from 1970, where Yamamoto published on this reaction where you have this nickel-2 complex by pyridine ligated. So now we have a cis configuration on our metal center. You dissolve this in chlorobenzene at room temperature. What's going to happen? Yeah.
You reductively eliminate butane and then oxidatively add the chlorobenzene.
Yes. You reduct eliminate to form a nickel 0. Correct. This is driven by butane that's going to boil off. And then you have a ton of chlorobenzene around. It's going to oxidatively add there. So here we have the last two steps. We have reductive elimination, oxidative addition. So now someone just has to pick up the pieces and put it all together using the metal as a catalyst. And that's what Kumada did in 1972. So just 2 years after this reductive elimination oxidative addition with nickel was used. And as you can see, it's nickel that is the first metal that was used here. So the so it's most people will just say Kumada coupling, but like technically Kumada Kurio coupling or Kumada Kurio. You know, you can build a lot of names in some of these reactions. But they found this catalytic nickel, just 0.7 mole % of this DBPE nickel chloride can catalyze the reaction, giving 80% of this carbon-carbon formation. Yeah, the reaction can also sometimes be done with lithium, but it's most common done with magnesium. And as you can imagine, using a Grignard reagent in your cross-coupling, functional group tolerance is not going to be great. That's the downside of the reaction. The good thing is it's a really fast reaction mechanism. Like the transformation is extremely fast, and that's the general limiting step. So it's really fast, very robust. And that means that you can sometimes actually tolerate more functional groups than you would think using a Grignard, because the catalysis is just running so fast. And then because it's also very robust and fast, you can do like really sterically encumbered bond formation, such as this right here, which is a modern example where other couplings would have a difficult time because of the sterics here. The Kumada coupling actually works really well. And you should have covered the synthesis of magnesium compounds in the main group. But just to maybe refresh, what are some good ways to make organomagnesium reagents? Yeah. Yeah. So
Metal and your corresponding aryl halide or alkyl.
yeah. What's another good way?
Transmetallation from like organolithium.
Yeah, you can do transmetallation. That's also, if you have heard about the turbo Grignard, those can also be used to kind of transmetallate from one commercially available magnesium reagent onto the desired aryl halide. All right. So that brings us to problem number 1, which I tried to draw out here. So take a minute to just take a look at the problem of the day. It deals with how to get on cycle from palladium 2 down to palladium 0. So take a minute, maybe talk to your neighbor to discuss these different pathways. Okay. Well, I don't know who this- That's intimidating. Everyone had a chance to look. I don't see anyone talking to the neighbor. Everybody is good with going through? Talking about this? All right. Well, I'll pick a name then, and then we'll see. Oh, I know who this is. Al. Can you go through the first one? Then we can yeah, pick another one for. So the first one is palladium chloride, Grignard reagent.
Can you call this a transmethylation? Just that you form palladium aryl chloride and then do a reductive elimination.
So it has let's just write the actual excess of Grignard. So you said transmethylation. Let's do
Yeah.
that.
And then reductive elimination to form aryl chloride. Oh wait.
So if you
Biaryl, sorry.
yeah, so you're gonna transmethylate twice.
Then form magnesium chloride.
Plus the salt. And then you said reductive elimination. And I get palladium 0, right? Yeah. All right. So pick another name. Sebastian.
So I think this one you have, I think you do dissociation of, I think, one of the chlorides and then replacement with an acetate. Or
Let's write that out first. Okay, so you're saying. Let's put an acetate on. All these things. All right, so we're here now.
then from there, I guess you could just do your reductive elimination. Oh no, well, I guess the geometry is incorrect for that. So do you do a do you make like you don't make the bridging like 8 to 2 complex, do you?
No. Yeah. But it forms something, so if you think about this, it's, what is like the strongest reductant in the system?
Your phosphine.
Yes,
So
so that's probably gonna be involved. And then we also have your SJ here, right? It's gonna kind of be set up.
so do you extrude out P5 and then do the same thing twice? You get
It's
out.
gonna do it once.
Oh, okay.
Yeah, so now you're palladium 2, and you know, that to palladium 0 plus your that will edit it correctly, and then probably with a little bit of water around, you're gonna hydrolyze it and get the phosphine oxide, which is gonna be the driving force for this. Yep. All right. Let's talk about the last one. Fran? Okay. Let's see. Unless we have a volunteer, you can always volunteer, that's fine. Amy?
Do you do, I mean, deprotonate and use hydrogen gas?
So what would you expect if you just mixed? So let's just. If you have triethylamine, rhodium acetate.
I just read it actually. Or is it just?
But what, well, I was sort of really anything that's to deprotonate, right? At this
So
point.
it is too, like.
Yeah, so maybe not necessarily like now it's acetate X type is gonna be L type. So it's the probably gonna exchange it, but it's definitely gonna coordinate. Yeah. So let's coordinate. Ethylene on there.
And palladium.
Sorry.
Can palladium deprotonate that?
Protonate or
Or beta hydrogen.
so we have probably enough to decide here. So you're gonna have these two need to be coplanar. You talk about this, yeah. So coplanar, you're gonna do feed hydrogen elimination. Get the palladium hydride. This is two acetate on here. And base or ionosphere. Yeah, so true, this is ionosphere. It could also be ionosphere, but and then a base here will get you down to palladium 0 plus. All right. These are the most common ways of getting on cycle from palladium 2 to palladium 0. There are of course other ways, but these are by far the most utilized. Any questions for this? Nope. All right. Well, we'll move on from magnesium to zinc. Was there a question or no? All good?
All good.
So, the next one we're going to talk about is the Catalytic coupling. And here is maybe some of the first work that was really where you really switched to palladium. And maybe one of the reasons for this is because they were really interested in polyene synthesis, so forming these types of compounds. And with nickel, these nickel alkynyl species are not necessarily super stable. They kind of undergo isomerization, so you can't really form, if you wanted to form these bonds specific with different R groups, then what's the problem with nickel is that this nickel alkynyl can isomerize the two R groups, so you have a different configuration here, and that's gonna mess up if you wanna form just one product. Mechanistically, I think one way to think about it is that you form this NO2 complex where you have the double bond kind of coordinating into nickel, so that allows the rotation. You can also think about it more as like a carbonyl type of formation that allows the double bond to be more single bond character, and that allows rotation. So that may be one of the reasons why they switched to palladium here. And magnesium was really the first that moved away from magnesium into actually first aluminum, later to zinc. So this coupling was published in 1976, where you have this aluminum species, you react that with alkene iodide, palladium, get 70 to 80% yield of your desired product. And quickly, just how do we form this reagent? Anyone knows? Has a guess? Yeah, you start from the alkyne, treat it with dibol, you get to your aluminum reagent. Unfortunately, these aluminum reagents have very poor functional group tolerance. So that's why they moved away from this to zinc. And a key observation that they made was that when they tried to do this coupling with an aryl iodide, they did not observe any product unless they added zinc chloride. So after a week, this poor student still had 0% in his reaction, or their reaction, and they're adding zinc. It was done within 1 hour at room temperature. So what's going on? Well, we now know that the aluminum switched with zinc, and this is a very potent, good transmutating reagent. And I gave you. And then just for a maybe a more clear example here, the canonical Nikishi coupling of aryl halides or alkene halides with your zinc organozinc reagent gave good yields. This was published actually before this observation, so I'm not sure what exactly. But just as an example of like some of these key observations that were made really led into like this huge evolution of a certain type of cross-coupling that ended up getting the Nobel Prize in chemistry years later. An important aspect of Nikishi coupling is, of course, making these organozinc reagents. You can both use organozinc halides, but also diorganic zincs. If you think about reactivity, the diorganozincs are significantly more potent transmutating partners, but also a lot less nice to handle. So we can go through a little bit of synthesis here again. Does anyone know how to make some of these organozinc halides? We kind of touched upon a few methods already. So the first, I think we've talked about numerous times now, transmutation from another organometal reagent will form your organozinc halide reagent. What is the other way? We also talked about this briefly.
Direct oxidative addition from
Yeah.
zero valence zinc.
Yeah. So activated zinc powder, your aryl halide of choice, will give you your desired reagent. The diorganozincs are a little bit more maybe tricky to form because you need to really drive that second organo component on. Does anyone know any syntheses for these?
From like poly-substituted organoaluminums. Or I think that Noshell, I just remember Noshell did one thing where you do a lot of sonication. And
Yes.
I don't remember much beyond that.
Yeah, so Noshell has done a ton of work in this in very recent years, trying to get to also put different like kind of ligands on zinc to really stabilize these reagents, make it more shelf like storage friendly. You know, we make these in solutions typically, and you don't necessarily want to store this around everybody's comfort, sure still. So there's for sure been like done a ton of work on these, and yeah, Noshell has been one of the. But you're in on some of the correct. I think this is number 2. So I'm just gonna go through number 1 first, and then it's not with aluminum, but I'm sure you can also do. So the first one is actually just to drive the equilibrium here. So from this synthesis, you can actually drive it to the diorganic zinc. You just need to precipitate. You need something to drive the precipitation of this. So it's typically you use the cyclic equilibrium. If you have a magnesium here, you can add dioxane, it's gonna crash out, and you can drive it to the diorganic zinc. Then the second one is kind of what you mentioned in that ROM you use boron though. It'll be a little bit easier. This diethyl zinc is readily available, so you can do this transmutation, and the driving force is the boron that will is a gas. And then finally, I think this is maybe not intuitively, but you can do these iodine zinc exchanges, and that's some of the work that Noshell has looked into. Some of the work, it's more efficient if you add a copper salt as well to these to kind of drive it, and the mechanisms are kind of some of it is radical based and so on. So but there's a lot of work in this realm, and I think it's definitely made the Nikishi coupling maybe more pronounced because it is a really efficient coupling. All right. I don't really know which one. Okay, so the next coupling we'll talk about is the Nikita-Stille, commonly just referred to as the Stille coupling. And both Megiddo and Silly published on this, and I think they really drew inspiration from this example by Eborn. Poor chemist in 1976 actually kind of reported the first example of a coupling using tin as a transmutating reagent. But maybe it wasn't really realized here. So let's go through what's going on here. You have an aryl bromide, this tin reagent, palladium. What's going to happen first? Someone said oxidative addition? Yeah. You have palladium 0, oxidative addition. What's going to happen next?
Transmethylation.
Yes, transmethylation. This is very similar, I think, if you have run into the Miara correlation. So you do transmethylation with this, get to this palladium 2 species. What is going to happen then? Reductive elimination. And then you have your tin reagent in situ, and this is going to meet another oxidative addition complex, and it's going to transmethylate. So yeah, even reported on this in 1976. Then in 1977, Megiddo published this ketone synthesis where you start from an acyl chloride, tin reagent, palladium, and you can form the carbon-carbon bond. And I think for this example, it's kind of been debatable or discussed whether this exactly is like kind of tapping into the standing type of couplings, because using an acyl chloride kind of makes the mechanisms a little bit more murky. And Stille really published like going from the aryl halides with the tin, again, tin reagent, palladium, and you form the carbon-carbon bond. So it's much more clear type of chemistry to use milder conditions and a lot of mechanistic studies. So I think that's maybe why most people just refer to it as the Stille coupling. And this was, very similar time as well as needed at the acyl chloride. All right, let me just see that I have. All right. So key point about the Stille is that when that was developed, the functional group tolerance went up significantly. It's a way better, at least in terms of functionality, way better coupling than the previous ones that we talked about. And then an awesome feature is that you can install your tin really early on in synthesis. You can carry it through oxidations, HWEs, and it will continue to just be sitting there ready to cross couple at any time you wish to do so. That's a really awesome thing about tin. They're air and moisture stable. The downside of it, and maybe why people are not necessarily grabbing their tin reagents from the storage room, is concern of toxicity. This is debated by people that are working with these couplings, and there's been a lot of work to try and mitigate and understand the toxicity of these types of reagents, but it is, for the most part, in the community still a concern, especially if you want to run these reactions on scale. Okay. So we'll talk a little bit about the transmethylation and how to facilitate faster transmethylation, because the transmethylation between zinc and palladium is actually quite slow. So there's been work done here to try and facilitate that. So you can modify the ligands on tin, or you can add copper. What's going to happen is copper is going to pick up the organo component, and then it's going to transmethylate to palladium, and that transmethylation is more facile. So we're going to see an example of this here with this carbastanotrain. We have this big, nice ligand on tin with a nitrogen that can donate into the tin. That means that you have a faster transmethylation because you're kind of weakening the tin methyl bond, setting it up for the transmethylation step in this coupling published in 92. And with this strategy, enantioselective examples have been published, and that brings us to also chemist of the day. But before we go through that, maybe we should just talk a little bit about the synthesis of these types of reagents. Does anyone know or have any good suggestions on how to get to this translating partner? No one has done this chemistry.
If you do it at low enough temperatures, you could imagine that your R1, R2 compounded, you could take a chiral halide, and if it's like -90 or something, you can retain chirality and just add it to the stable chloride. I wouldn't want to do that though.
Yeah, no, you kind of want a very modular like approach, right? You want to be able to install a ton of different functionality from R1 and R2. So you want to kind of get back to something that's you can easily just think in one step add in. Did you have a suggestion?
You do hydrostanylation?
Yes. So we'll go back to that. So you have a if you just go one step back, you can start from the chloro staining, and if you lithiate here, it's going to act as a nucleophile, and you can essentially do essential tech chemistry. So going back to just like a very modular building block. So how do you get to this? Well, one way is at least to do toss in tin chloride and Schwarz reagent, so zirconium hydride. I think it's the most common way, but you can think about other hydride sources to get to this. I saw an example with Grignard, but essentially the same thing. Yeah. Okay. So the chemistry here in the coupling is an interest specific coupling published by Bisco in 13 using palladium 0 Jackie phos, which is drawn out here. And which brings us to chemist of the day. Does anyone know who it is? Maybe there's a little hint in the name of the ligand. Jackie or Jacqueline Hicks works at Merck now. She developed this ligand when she was postdoc in. Anyone has an idea with this looking at the ligand?
Sorry.
Buckwald, yeah. In the Buckwald lab, this biphenyl phosphine backbone of the ligand leads maybe our minds back to the Buckwald lab. So she developed this as a postdoc with these, and obviously not for this reaction, for a Buckwald-Hartwig amination using very electron poor amides, but it's found uses across different types of palladium catalyzed couplings. And she did her PhD with William Roche at Michigan, who is now emeritus professor at the campus in Florida. So kind of a cool little fun fact, I guess. All right, so in the coupling, they also use copper chloride and potassium fluoride. Does anyone have an idea of why copper chloride would be used here? Or why you would, sometimes when you see these copper salts. Sometimes copper salts can be added to kind of scavenge the phosphine ligands. So if you have a bisligated palladium species, the copper salt can kind of pick up one of the ligands in this equilibrium, and that exposes the palladium much more, so you can really set it up for oxidative addition. Something to keep in mind as you look through literature. And then the potassium salt, potassium fluoride, important that's fluoride.
It's gonna jump.
It's gonna, oh, that's the active form, yeah. It's gonna form the 8 complex. So addition of fluoride into your ascending reagent sets it up as a much better transmellation partner for the carbon down here. So that's to activate that. And I think we're gonna see a lot more of 8 complexes here in the next few slides. So we're gonna move on to the Suzuki-Miura coupling. Really the workhorse reaction of these transmelating reagents. This is one of the reactions that is the most utilized in industry. It's an extremely robust, fast, and it has a high degree of functional group tolerance. So the first example here from 1979 you do the hydroboration to form your transmelating reagent, and then you can cross-couple with palladium. You need base, typically alkoxide bases, to, again, I think there's a little, to activate your boron for transmethylation using the same analogy to just what we saw in the stele, so forming the 8 complex here with boron. And that's going to allow a more facile transmethylation with palladium here. And this has been studied in detail if you're interested from the Denmark lab. So this coupling requires space. There are examples in literature that say, oh, it's base free, but in principle, you're just incorporating your base into your conditions in a separate way. So it does need to go through this 8 complex in some aspect. A lot of work has been done with these different types of boron coupling partners. So we'll talk a little bit about that here in the next problem as well. Here I've drawn out some of the more common coupling partners, ranging from the boranes from 9-ppn, where you do the hydroboration. These are not, what's nice about, I guess I should mention that what is really nice about the Suzuki coupling is that these boronic esters and acids are typically bench stable, so you can keep them around. And with the Miura correlation, you have readily access to them. And it's really built up like a whole infrastructure of how to get your hands on these boron reagents, which wasn't there before this cross-coupling really picked up the pace. So if you want to do any alkyl, the 9-ppn is a really good reagent. You can do the hydroboration with alkenes, terminal alkenes, and it's selectively for their terminal position. So you get just one isomer that you can then cross-couple with. Downside is it's not super stable. You kind of have it in solution, kind of like the zinc reagents that we saw earlier. What's most commonly used are these boronic esters and boronic acids. There's a lot of different types of esters, and they can behave differently in catalysis, but I think if you're familiar with it's like somewhat of a common Suzuki coupling, whatever, like esters on there is probably gonna do the trick for you. Unfortunately, at least for some reagents are not the most stable reagents. They undergo hydro deborylation. So that's why maybe one of the reasons why these trifluoroborate salts were developed. These can be stable for some of the reagents that are not stable with the boronic acid. They're stable for the trifluoroborate salt. This trifluoroborate salt will hydrolyze in your reaction mixture to the acid, and that will then transmethylate. So it's kind of a slow release of your active reagent in your reaction. And then as we move to even more stable boron reagent, these masked borons that Kira's called them here, the DAN and the MIDA, they're more, you can think of them more as like protecting groups for boron that you can kind of put on to make sure that it you can carry it through, and then you need to kind of deprotect it prior to coupling it. There are a few examples, but where these are directly used as transmethylation partners, but most often think of it as like a protecting group. Okay, so this brings us, I think, to problem number 2 on your notes. So please have a look at that. I'm just going to draw it up and then we can talk about it. Yeah, so problem number 2 deals with rate of transmethylation, and maybe it's not intrinsically obvious which ones are going to transmethylate first and which ones are faster. It's still, you know, being investigating literature, there's a lot of complexity to this, but we're gonna discuss a little bit about it and then see where that takes us. Let's just draw it out. Does anyone have any thoughts they want to share? I don't think it's not necessarily obvious which one's gonna go first, and but maybe we can just talk about some of the factors that may influence the rate of transmethylation.
I think maybe
Mm.
your boron complexes that have much more strained carbon backbone are going to increase like propensity for an oxidative addition event. So I maybe say that something like D would be faster than A. Interesting. That is my guess.
Yeah. So I can see where you're coming from with like thinking about the strain and how much like how the oxygens are kind of tied back and how that like allows boron to do to interact. I think something that you maybe did not consider about D is maybe the steric bulk that you're introducing with all these methyl groups.
Yeah, I guess overall it would be quite bulky.
Yeah. And I think that is as I said, it's not obvious which one of these necessarily, but I think one thing that you can think about when you look at the translating reagents is consider the sterics that is going to create around the palladium center as you are in the translation step. So actually D is quite slow. Does anyone have any other thoughts they want to share? So D is actually the slowest. Let's write it up a little bit. This is called D, and it's also depends because of the pinnacle, the dial that you make it from. All right, so that's the slowest. Yeah. If you think about like, just think about sterics. What do you think?
Then if I'm just thinking about sterics, then I would say from slowest to fastest D, C, B, A. But I don't know if there's maybe an additional effect that like the 5 versus 6 membered ring has.
Mm-hmm. Yeah, so you are correct that B and C. So B is faster than C, because you have less sterics. It's not by much as far as I remember. I just looked at the paper yesterday, but so that I can also say that the boronic acid is actually not very fast. Actually, the esters are faster. Some of them, at least. So it's the acid, and then you have this is the net or the top neopentyl from the diol, and then the fastest is the ethylene glycol derived. And as I said, it's not like intrinsically obvious why this order is as it is. I think so. We talked about sterics is a big factor here, but something else to consider is the propensity for the boron to want to undergo hybridization, because it's going to form the 8 complex, and that may not be just by looking at the structure directly obvious how exactly you want the oxygens to allow for it to want to go into the 8 complex, but you also want electron with like the inductive effect of the oxygens because you want to form a more carbogenic carbon so that you have a faster translation. So there's a lot of factors going into this. The work here is based on, do I have it on the slide? No. Based on work by the Denmark group. I guess I should I can write up the reference, which I think I have here. The Denmark lab has done a lot of work on studying the transmutation of boron reagents. And for this work, as you may also imagine, running these reactions -30°C in situ NMR monitoring is not an easy task. And I think even looking at, like, they also mentioned some of the challenges that they have in doing these types of kinetic studies, and that the kinetics are not always super clear. Another thing to consider is that these boronic esters and acids have different solubilities, so you're going to change your concentration, and all of this is going to create very, very challenging systems to study. But if you're interested, I will just write the reference over here. I think I have it. Here's notes. This is directly from this study, and then in this they also reference a lot of the earlier work on these types of studies. So if you're interested in this, turn to the Denmark lab. They've done a lot of beautiful work.
Hey, Anna,
Mm-hmm.
wait, can you just hear me rephrase why the acid is slower?
Yeah, it's not necessarily clear, and I didn't go into the specific of why it's a lot slower. I think it's just something about how the oxygens are kind of tied back for the other ones that allows it to interact more easily. Yeah. Okay, any other questions for this? Nope. All right. Okay, I think I also have. All right, we're gonna then turn to silicon, or the Ravn coupling. It's in many ways you can draw like tie it back to the Suzuki coupling. Just here we have a silicon that's going to be a transmutating partner. Recording 88. It's underutilized. It actually has a really broad functional group tolerance. I think they just discovered it a little too late because the Suzuki coupling had already picked up. They're doing all these boron reagents. The reaction worked really well. And as someone then comes up and say, oh, we can also use silicon, maybe people didn't pick up necessarily the speed that didn't pick up the same type of excitement about this coupling. Also for the Suzuki coupling, the ligand scaffold had already kind of been like mapped out, and it's kind of starting over as you look at a different transmutating partner. But the reaction works really well. It has high functional group tolerance. It does require fluoride addition. Maybe strictly speaking here, it's a Ravn coupling if it's using fluoride as a promoter, and a Ravn Denmark if you avoid using fluoride. A lot of what else would I say? Typically, people will say that like you need fluoride for the silicon to transmutate, but there are studies. Again, we're gonna look at the Denmark lab that has studied the mechanism of this reaction, and they found that you can form a different type of transmutating agent. But before we look at that, let's just look at the active form of the silicon transmutating partner. You add fluoride in, you form your 8 complex, and that's going to transmutate. What the Denmark lab then contributed with to this is that they found that this type of silanolate coupling partner can also transmutate. So that's why I say if it's without fluoride, it's more of a Ravn Denmark. But I think it's kind of, people will say Ravn Denmark, and it doesn't necessarily. But strictly speaking, you don't need fluoride, but you need a very specialized translating reagent in this selenolate. What they found is that you can go through this type of translation. So the selenolate is kind of already set up to interact with your palladium, and that allows translation. That brings us to the Sonegashira coupling. If I don't have anything else, let me just double check. Yeah. All right. The Sonegashira coupling is it's coupling between an alkyne and an aryl halide. Using a unique dual catalytic system, you use both palladium and copper. There are examples where you don't need copper. Palladium can do the whole shebang itself. But then you're actually talking about a different named reactions, the Heck alkynylation. So if it's palladium, copper, Sonegashira, the catalytic cycle looks very similar to what we've seen, but there is a little caveat with the copper. So you have palladium 0 doing oxidative addition, transmetating with this copper acetylide, and then reductive elimination to form your product. Copper here is facilitating the deprotonation of your terminal alkyne using the base to form your active transmetating partner. Very robust reaction, gives excellent yields in like 99% of times. I spent most of my undergraduate running these reactions, and they're pretty awesome. Really, I mean, your product almost just precipitates itself, and you like you just concentrate it and you filter off your palladium, and yeah. Anyone else run a lot of Sonegashira reactions? Yeah. You're a fan? Or no?
They're very good.
They're very good, yeah. They're very good.
Reactions I've done here that consistently worked.
Yeah. Even if it, you know, a lot of it's like, oh, be careful with air and stuff. I feel like this can almost run. Not totally there, but it's very robust. Okay. Last thing in the carbon-carbon bond forming reactions are the alpha relations. Here we have a deprotonation of a alpha to a carbonyl to form your enolate, and that is then used as a transmetating reagent to form carbon-carbon bonds. So here you form quaternary carbon centers next to a carbonyl. Like that's at least like really what have driven this reaction is that you can form these very sterically bulky center with NH2 selectivity if you have the right chiral ligand in your mixture. Need strong base or somewhat strong base to deprotonate here. Sometimes this deprotonation, you kind of do it prior to then dumping everything down in your reaction mixture. Published in 98 by I think by Buckwell and Hardwick almost simultaneously. As we'll see in a minute, that is a theme for the last part of the lecture. Yeah, and then you form sp2, sp3, carbon-carbon bond in these types of reactions. Okay, any questions to the carbon-carbon? Anything? Maybe. Otherwise, I will move on to carbon heteroatom bond formation. In these types of reactions, we will see very similar events as we've just went through in the carbon-carbon bond forming cross-coupling reactions. We have oxidative addition. We have formally a transmethylation. Now, as we move to heteroatoms, we'll see it more as maybe a ligand exchange followed by deprotonation before you get to your reductive elimination to regenerate your active catalyst. So moving to heteroatoms in this formal transmethylation step, it's significantly more challenging, and you can get off cycle more readily. So ligand scaffolds are really important here and has played a huge role in order to bring these reactions to an efficient and modular systems. The first or early work on forming amines using transition metal catalysis was actually published by Megiddo, who we met in the Megiddo-Silly coupling using tin reagents. So these tin amides, they found that they could use as transmelating reagents to form these anilines, but the result kind of went underappreciated at the time, maybe because of all the cross couplings, like the carbon-carbon cross couplings that were at the time. But it was then picked up later, and then you kind of know the story from the Buchwald-Hartwig emanation work. So we'll see the evolution of that. But there was hints about this otherwise unprecedented reductive elimination of a carbon-nitrogen bond already back in 83. And I think maybe the audience here will also appreciate that the Boger lab reported just a year after an early example of a stoichiometric study of a CN reductive elimination. So maybe we can go through this a little bit. I think we're on time. So you use this in the total synthesis and stoichiometric palladium here. What's gonna happen? It's palladium 0 already. Oxidative addition. Okay. Into the bromide. So palladium sitting here, there's nitrogen right on the other side of the phenyl that's going to coordinate, and then can reductively eliminate with base to form this structure. So here already we have hints about this reductive elimination occurring with heteroatoms, but it's not really picked up until a decade later in 84, where Hartwig and Buchwald independently, but in the same issue of JACS, published follow-ups to the Megiddo work. So let's take a look at the early work here from Hartwig and Buchwald. So Hartwig published more on like the mechanistic side of things. His interests were more to isolate intermediates and to really show this unprecedented reductive elimination, and that the Megiddo system did go through oxidative addition transmethylation with this tin amide to form the desired product. Whereas Buchwald was maybe more interested in the synthetic application of this transformation. So he published a more convenient synthesis to form these tin amides using a very commercial available tin amide. You can mix that with your amine. Argon purge will release the diethylamine, and then you can dump in your transmelating reagent to your palladium catalysis. So he kind of like expanded the synthetic application of the method. And then the year after, again, almost at the same time, the two labs published a tin-free conditions for this type of cross-coupling. A key takeaway here is that we need strong sterically bulky base in order to avoid tin. Here, the Buchwald example, they use sodium tetroxide to form the aniline product here. And in the Hartwig case, you use lithium HMDS to deprotonate and get your desired cross-coupling. So through literature, it's kind of a lot of back and forth between these two labs. They published a lot of different types of work on this, on these types of cross-couplings. And then in 2006, they published together with Donna Blackman on a more detailed mechanistic study of these cross-couplings. So I've drawn out the catalytic cycle so we can talk a little bit about the individual steps and how this reaction is taking place. So you have your palladium precatalyst, you get to palladium 0, as we talked about today in problem of the day number 1, oxidative addition. We've seen this before. Then you have your amine coming in. What's going to happen here?
ligand exchange.
Like an exchange with which one? With the bromine? Everybody agrees it's a bromine. What's gonna happen if it's the bromine? So bromide is X type. This one is what? At the moment?
It's L type.
L type, yeah. So you form like a cationic complex. Maybe it doesn't seem to.
Maybe a base around.
Yeah, the base is involved a little bit later. We're just trying to toss in a me here
Exchanges with the L type.
with the L type, yeah. So you're gonna, I don't know why I think this is gonna work. So you end up here. And that sets it up for the depronation step that we maybe wanted to do before, but we need a soft depronation. So that means that you have coordination to your metal. It's gonna acidify the proton. You add in your base, and you get to this that I've had to draw out because Kiri had made a little hint about what these off-cycle species may be. So you get to this that's set up for reductive elimination. However, there's a few pathways this complex can take which are not productive. Does anyone have any suggestions of what could be a potential liability here?
Those conditions.
Yeah.
You do beta hydrogen elimination on.
Yes, that was the little hint that Kiri had given here. If you have an alkylamine, you can be set up to do beta hydroelimination if you have a site to do so on palladium, and it's gonna give you the palladium hydride complex down here. So it's gonna be off cycle. And then you have your imine, which complicates the whole system. Then that's irreversible. Then there's like a back and forth here. What could that be?
This trans-isomerization of ligands.
Could be, yeah. The trans is not going to reductive eliminate. Yeah, you can coordinate another amine. You have excess amine in your mixture. We just saw that can coordinate to palladium L type. That's what it's going to do here. And this, these types of amino palladium complexes are not catalytically active. So it needs to go back to this in order to reductive eliminate. So as you can see, that this is maybe also some of the reasons why there's been a lot of work in finding ligand scaffolds that can accommodate these challenges that you end up in when you couple with a heteroatom. Okay, that brings us to problem number 3 of the day. So take a look at the problem. We're going to look at the reductive elimination of the carbon-nitrogen bond. And the relative rates for dialkylamines is faster than arylalkylamines. That is faster than diarylamines. So we're going to maybe find a few explanations of why this could be. And then talk about what type of experiments you could do to probe these hypotheses of reductive elimination rates. Yeah, take a minute to talk to your neighbors, or think about it yourself, talk to your neighbors, and then we'll discuss a little bit about this. We need to take the names out. Otherwise, it's always the same. There's kind of two arguments for the first, for A here. The draw name, was anyone interested in chiming in what they talked about? Or should I just randomize? Okay, I'm gonna draw a name since nobody is saying anything. All right. Well, I draw Fran again. Fran, you're a popular choice in this. Okay.
I think she saw line hands.
Oh,
Fran, would you mind to?
May, my Teely or May Teely? How do you? My Teely? Oh, online? Oh, sure. Okay. Oh, yeah, so a name. It's David. David's here. Oh, yeah, yeah, you're David? Okay, okay, I was like, I don't know who David is, sorry, yeah, go ahead, David.
Look at the question.
So, the question is, possible explanation for the trend of alkyl, dialkylamines being faster in reductive elimination than aryl alkyl, which is again faster than diaryl. It's okay if you're.
I would just go with the same explanation that was already stated, that it's more basic, so it's easier to protect it.
Yeah, that's point number one, is that the amines with alkyl groups are more nucleophilic. So it's gonna be easier to do like the attack on the ipso carbon of the carbon group. Yeah, so that's point number one. Yeah, that's actually written down. So the nucleophilicity of the alkyls is going to make the reductive elimination faster, because you have more of more donation into the carbon, the ipso carbon that you're going to reductive eliminate with. That was point number one. Great.
Can I ask a question?
Yeah, of course.
If you have a more basic nitrogen, would that increase the sigma donation to the palladium? But I feel like if you increase the sigma donation to the palladium, it will make it more electron rich, which wouldn't. I feel like for adaptive elimination, you want a more electron poor metal. So it's kind of
Yeah, it's a little counterintuitive, I agree. So I think there's you bring up a good point. Like, you have a better sigma donor in an alkyl amine, so you have more donation. It kind of taps into point number two. So I think when you think about like electron poor metal to do reductive elimination, you typically talk about also the ligand, because here you are talking about the groups that are gonna eliminate. So it kind of complicates the system a little bit, yeah. But it is a good point that you have more electron donation because you're more electron rich, which also means that this bond is gonna be,
Quicker.
yeah, so shorter,
Longer.
it's gonna be a bond, so you have less. All right, let's think about this.
Oh.
You have your, because it gets a little, if you have an aryl group, it's gonna withdraw more electron density. It's gonna polarize the bond more between palladium and the amine. If you have a more polarized bond, you have a stronger bond. So for the diaryl, you're gonna have a stronger palladium nitrogen bond. Because you have more polarization. Okay? So that means that if you have your alkylamine, you have a weaker bond. Because you have more donation, you have a less polarized bond. So you're gonna have a weaker palladium nitrogen bond. And if you think about it in terms of ground state energy, if you have a diaryl, it's gonna have a stronger bond with palladium, so it's gonna be lower in ground state than your alkylamine. It's gonna be a little bit higher in ground state energy. That means that the barrier to go to the transition state for reductive elimination is gonna be a smaller, like delta double G double dagger, right? So that is point number 2. Which I can try and so it's less polarized palladium hydrogen bond, which leads to let's see, energy higher. Does that make sense? I think you might have to write your notes on this point, but everybody is following the logic here. Yeah.
Wait, this might be a really dumb question, but I guess I don't understand why those things are different. Like, I would think that the second one is just also helping the reductive. Like, are they just 2 steps that both help the reductive?
So you can think about it like the nucleophilicity is going to impact how high energy the transition state is,
Okay,
and this one is going to influence the ground state, like
Okay.
prior to the transition state.
okay, so it's just like.
So it's just like it's 2 factors that it can be at least hypothesized for the trend that they observe. They're like related, but they're not the same.
Okay.
Yeah.
So like, I know it's an oversimplification, but could you just argue based off of HSAB, palladium's soft, amines are a lot harder, and especially when they're alkylamines, so it's gonna form a weaker bond.
Yeah, I mean, you can. Yeah, I think you can also.
It's essentially what you said, but yeah.
No, it's good to have different types of wording on it, because I think we all have different background in how we are taught, and what we talk about, so. Yeah.
Clarify which one has a polarized. Is it the dialkyl?
The less polarized one is the up. Yeah. Yeah. Yeah, so less polarized. Weaker bond. Okay. So second part of the question was any other questions, please, we can talk about. Yeah.
This is just, I'm still kind of confused on point number 1 because it's like, so I didn't realize that there's an ipso interaction. It's that only just with when you're reductively eliminating heteroatoms, because it's kind of like you don't really care carbon-carbon bond. Yeah, okay, it is like that. I got
It's
it.
like this, right? And you're gonna push these together. They're gonna like kind of form a bond, kind of break these 2 bonds.
Yeah.
So it's in that like transition state.
Yeah, but this is unique to like heteroatom reductive elimination, right? If you were to take like an aroboronic acid with another one, like you don't really draw that. I mean, in the transition state, you have that bond forming, I guess.
Yeah.
Okay, I see it.
Okay.
I feel like in terms of carbon heteroatom reductive elimination, you typically think of this more of more polarized transition states.
Mhm.
Whereas if you reductive eliminate carbon-carbon bond, they're like kind of just approaching each other. in this case, your nitrogen is approaching more to the carbon first, and then your palladium nitrogen is
Yeah.
diminishing.
Yeah, because I mean, you have more electron negative atom here than here, whereas carbon, like, they're the same or very slight differences.
Well, like,
So,
yeah, I mean,
yeah.
the carbon still works better, right, when the electronics are biased, so I guess like
Yeah.
that's kind of the same reason.
Mhm. Yeah. Okay, does anyone have any ideas based on what we maybe also just discussed on how to maybe distinguish among these hypotheses? Like, can we test one hypothesis without kind of influencing the other one? Yeah,
Just stick a bunch of methoxy groups on the arrow of the aniline, see if that increases the electron density on the nitrogen and reverses the effect.
on the arrow of the,
So on R1 or R2, if you stick a para methoxy on, that's going to increase the electron density on the nitrogen. So you'd expect it to then increase the rate
yeah,
of
so then you would
determination.
compare the diaryl amines across the board, but you wouldn't necessarily be able to compare that to the alkyls, right? Like, because you're changing.
Sure,
Yeah.
but if the hypothesis is that
But-
it's purely nucleophilic, it would be more nucleophilic. I guess it's just
Yeah.
easier to modify the aryl than it is to modify the alcohol without massively increasing the steric bulk.
Yeah. Yeah, true. Yeah. Yeah, there could be a way of looking at you're thinking the nucleophilicity, right?
I guess the alternative is you increase the nucleophilicity of the alcohol, but then if you're going to do that, go from like secondary or
Yeah.
something like that, you're going to it's going to be more bulky, so it's probably they're going to influence it as well, and then you've kind of screwed up your
Yeah. Yeah, there's a lot of factors. Yeah.
I mean,
Yeah.
couldn't you do a very similar thing on the alkyl series and just make substituted piperidines and then basically put fluoros or trifluoromethyls towards the end of it, and then you can use this to work out your second hypothesis about polarization of the overall complex. Because sterically they would now be the same if you just make a series of piperidines. Maybe you could do that. You would have to assume though that whatever electron withdrawing groups you have nearby are close enough to electronically influence the system and not sterically influence the system. And the easiest way of doing that would be by putting it into conjugation. But now you are no longer looking at alkyl or, yeah, so.
Yeah.
That would be kind of tricky.
Yeah, and I think it bring up a good point is that the system is kind of convoluted by the fact that nitrogen has these lone pairs that really influences these two factors. So a way to kind of get away from that is to not look at nitrogen anymore. So if you look at the carbons, you're gonna get away from this lone pair that's gonna convolute things, and then you can really look at the influence on electron withdrawing character on the alkyl. So that's what people have done, is that they have correlated the rate of reductive elimination with carbon, different substituents on carbon, to then relate that to the point of the polarizability of the bond. Because as you withdraw electron density from your carbon, is it then going to influence, if you have electron withdrawing groups, then you have a stronger bond. So we just talked about the palladium carbon bond or nitrogen bond will be more polarized, so it's going to be stronger. So reductive elimination is going to be slower. And if you have the opposite event, then of course it's the other way, vice versa. So that's what people have done, is actually go away from nitrogen and correlate these trends with the carbon trends to avoid this complex nature of the lone pair on nitrogen. And I do think I have if anyone is interested, just for a reference, because since written by Hartwig, where he discusses these and also has a few references to some of his group's work in trying to understand these reductive elimination rates. Okay, we're running out of time, so I'm just gonna quickly go through the last bit of slides here. As you might imagine, you can go from nitrogen to oxygen doing similar couplings. Here, also again, Hartwig and Buckwell published on this. Key aspect here again is bulky ligands. Tritubutylphosphine, John Phos, just this again biphenyl phosphine backbone with tributylphosphines on the phosphines. And finally, the chain Lamb coupling, the kind of complementary reaction to the Buckwell-Hartwig coupling. What's nice about the reaction scope here is that generally the amines that work well for palladium catalysis, they don't work so well in copper catalysis, and the other way around. The amines that work well in the chain Lamb does not work so well in palladium, or more challenging palladium. So in this coupling, this is the example of an oxidative coupling. You have your two nucleophiles that you copper with catalytic copper base, terminal oxidant, both done with nitrogen and oxygen. The mechanism for these is a little complex and I think highly discussed, so we won't have time to talk about this, but one note is that it need this high valent copper to probably do this reductive elimination in this work. And then finally, the conjunctive coupling or three-component coupling, where you interfere the traditional cross-coupling of an electrophile and nucleophile with the Y. You can do that with CO to have carbonylations, SO2, very similarly, alkynes or alkenes to form more complex structures. And here is an example where you couple across an alkyne to form these highly substituted alkenes. And here I'll work from the Ingle lab, where you also have the same trend. You just cross couple across the alkene to form the diaryl product. So as you can see here, they're both like traditional Suzuki couplings and the coupling partners, but then you interfere the prior to transmolation. Typically before transmolation, you add in this insertion step, micro insertion of any of choice here, and you can form three-component coupling. And I think that's the last slide, right on time. Yeah, that was like kind of today's lecture. I don't know if you have if there's any questions, we can also talk about that after. Welcome to come down. Otherwise,